Hello, 7th grade. Hope everybody's doing well. Everybody's taking care of themselves right now during this time. Want to kind of cut the chit chatter today. We got a big lesson today, so get your notebooks out. Let's get busy. So today we're looking at Chapter 1, Lesson 3, Real Numbers and the Number Line. Kind of on a side note, guys, being left-handed, I tend to smudge when I write with pens. So let me know if you can see the notes with them being in pencil today. If they can, then we might go this route the rest of the year. So, anyhow, what we're looking at today, kind of a lot in one lesson. I wish it was broke up. But anyhow, we have a lot of vocab words. And our first one is the radicand. So jumping right into it, the radicand, that is the expression under the radical. And I've kind of got a picture that kind of shows this and this next definition. We also have the radical. And the radical is the symbol used when taking the square root. So if we look at this little diagram here underneath, this gives a good representation of the radical and the radicand. So the radical is, a lot of us just call it kind of like the square root symbol. The more proper definition for that is called the radical, and then what goes underneath is called the radicand. So if we look at number 1 here, 81, that is the radicand, and the square root symbol is the radical. So if we look at 81, we want to take the square root. That's what we're doing. We're taking the square root of 81. And anytime we take the square root of something, we should be asking ourselves, okay, what times what gives me 81? And we should go right to our multiplication facts, and we should understand that 9 times itself gives me 81. So the square root of 81 is 9. And that is because 9 times 9 equals 81. So it's as simple as that. Whatever is underneath this radical, all you're doing is you're saying, okay, what times itself gives me 81? Another way of saying this, guys, is saying, okay, 9 squared. 9 squared is also equal to 81. And that's because 9 squared looks like this 9 times 9. So the answer to the square root of 81 is 9. Moving on to number 2, we have the square root here of 64. Again, what times what gives me 64? Or what squared gives me 64? Well, that's going to be 8. So the answer to number 2 would be 8. And last but not least, we have number 3. Now this one's set up a little different, and that's because it's in a fraction form. It's no different than how we did 1 and 2, though. Take the square root of the number on the top, take the square root of the number on the bottom, and you'll get your answer. So what times what gives me 9? That's going to be 3. What times what gives me 16? That is 4. So the answer to the square root of 9/16 is 3 over 4. And number 3, guys, you couldn't even simplify this fraction because nothing goes into both 9 and 16 to even simplify it. But that's as far as we can go with that one. So the answer to that would be 3/4. And if you come over your calculator, if you hit this blue button, the second button, and then if you come down here, notice above the x squared, you see that radical or that square root. If you hit that after hitting that blue second button, you'll have the square root symbol pop up on your calculator. Just like what we see here on number 1, I could type this problem in, hit enter, and there you go. That gives you 9. So a couple ways of doing it. Next definition we have is called a perfect square. And a perfect square means that I can take an integer, and when I square it, it's going to give me some number. And those numbers are called perfect squares. So for example, on numbers 1 and 2, 81 and 64, those are both perfect squares. And that's because I have a whole number as my answer. I have 9 as my whole number for number 1, and I have 8 as my whole number for number 2. So any number that when you take the square root of it gives you a whole number, those are going to be your perfect squares. So for example, you could run through your list here. So 1 squared, that's going to be 1. 2 squared is going to be 4. 3 squared is 9. 4 squared, 16. 5 squared, 25. 6 squared, 36. So these are all of your perfect squares and so forth. And we could keep going and eventually get to 64, 81, and beyond even. But those are just some examples of what a perfect square would be. Now, it would not be a bad idea, guys, during your downtime kind of at home as you're going through assignments, you should know the square roots and reverse as well, so the perfect squares of numbers 1 through 25. Matter of fact, if we were still in class, you would probably have a quiz. But it'd be hard to monitor a quiz at home when you could type it all in your calculator, submit it to me, and then I have no idea if you know them or not. But you guys should know your perfect squares and your square roots of numbers all the way from 1 to 25 to kind of really help with this lesson and help as we move forward. Now those are examples of perfect squares. 1, 2, and 3 are. We're going to get into some problems that maybe aren't perfect squares. So if we look at number 4 here, we have the square root of 34. You should be looking at you should be telling yourself right now, okay, nothing times itself is going to give you 34. So we're kind of stuck in a rut here with this one. So therefore, we are going to estimate. So on number 4 and on number 5, these are going to be estimated because we don't know what exactly goes into, or what exactly the square root of 34 is. Whenever we estimate, we should pick between what two square roots 34 goes into, or 34 is closest to. So I know that 34 is very close to 6 squared, because 6 squared is 36. Now 36 is greater than 34, so I want what number is smaller than 34. Well, that's going to be 5 squared, because that is equal to 25. So I've got my two squares that are closest to 34. Which one is 34 closest to? 34 is closest to 36. It's only 2 away from 36, whereas it's 9 away from 25. So the square root of 34, it is about 6. And we would leave it as about because it's not exact. Same kind of procedures, guys, on number 5 as well. So the square root of 386. Okay, maybe you're not sure if something times itself gives you 386. So for that one, I probably would come over to my calculator, type that one in, because maybe you're not familiar with multiplication facts that high. Okay, it gives me a decimal. So I know that this one's going to have to be between two numbers here. So I can go through, guess and check, maybe try 15 squared, maybe that's not enough, so I can try 16 squared and so forth. Well, when you get this one down to it, it's in between 19 squared and 20 squared. And this is another reason, guys, why it's important to know your squares and square roots of 1 through 25. Because here we go, we're using 19 and 20. Well, the square root of 19 is 361. Square root of 20 is 400. So then I'm going to ask myself, which one is it closest to? Well, 386, it's closest to 400. So my answer here would be about 20. So not too difficult. Again, really important that you understand the square root process. You understand that the square root is simply doing something times itself to give you that radicand. What's underneath is the radical symbol, and then just kind of carrying that out. And then also important that you know those perfect squares for 1 squared, 2 squared, 3 squared, so forth, all the way up to 25, because that's going to help you answer some of these questions. All right, moving forward. Now our lesson's kind of broken up, guys, into 2 sections. So this is kind of the second section of your notes, and there's a bunch of vocab terms. So the first set of terms are these 3 words here: set, subset, and element of a set. So a set is a well-defined collection of elements. And all that means is it's a collection of numbers. It's a group of numbers that go together, or maybe are being paired up together. We then have a subset. A subset of a set consists of elements from the set. So maybe you have this set of numbers. You can group some of those numbers together to then form a subset. So essentially it's kind of a set of a set. It's a group of numbers that come from a set. And then the last word is element of a set, and sometimes you will see this as just an element, and that is just a member of a set. So maybe I have the set of all whole numbers, or all counting numbers. And those would be 1, 2, 3, 4, and so forth. This would be my set, because it's a defined collection of elements. And I could call this, I could define it and say this is my counting numbers. So that would be a set. An element in this set would be 1. Or an element would be 2. All it is it's a member, so it's a piece that's in this set. If I wanted a subset of this, maybe I could say all even numbers. So that would be another set that came from this set. And those even numbers I would pick out would be 2, 4, 6. So that subset did not include all of the numbers in this set. It only includes some of them. Moving ahead, we have some more definitions. And this is where we're going to kind of start to see, guys, the subsets and the sets and the elements kind of come together. So my first word is rational numbers. Let's see if I can get the whole definition on there. A rational number is any number that can be wrote as A over B. So it's in the fraction form of a number over another number where A and B are integers. And all that means is an integer, guys, it's not a decimal. It's a number that is a whole number. And B is not 0. So it's any fraction. A and B are numbers, whole numbers. B can't be 0. So in other terms, I cannot have 2 over 0 because B cannot be 0. So this denominator cannot be 0. So that would not be a rational number. Maybe 1 over 2. That's an A over a B. They're both whole numbers. B is not 0. That works. Maybe I have 3. 3 would be a rational number. Even though it's not wrote in this fraction form, if I were to write it as a fraction, it'd be 3 over 1. So it still works as an A over B. B is not 0. So it just kind of continues on and on and on. There's a bunch of rational numbers out there. Matter of fact, the list goes on and on and on. All right, kind of moving ahead now. I'll make sure I didn't lose you guys. All right, moving ahead. Our next term, guys, is a natural number. All right, I apologize. I think I lost you for just a minute there. So again, rational numbers, A over B, it's a fraction. Any number that can be wrote as a fraction. Even our whole numbers can be wrote as a fraction because the denominator is 1. Just make sure the denominator is not 0. Let's move on. Natural numbers. Natural numbers, guys, these are the numbers that you learned early on in life, back in kindergarten, first, second grade. Natural numbers are any numbers that are whole numbers and they're positive. So they begin with 1. So 1, 2, 3, 4, 5, all the way up to however far you want to go. Whole numbers. Whole numbers are the same thing as natural numbers, except for this time we're including the number 0. So again, it's a whole number, it's positive, and this set includes 0. And these would be examples of sets. The next definition is an integer. What separates an integer from a whole number or a natural number, integers include negative numbers. So integers are going to include -2, -1, and then they also include all the whole numbers and also 0. Our next definition is an irrational number. Irrational numbers cannot be wrote as a fraction. So an irrational number would maybe be, an example would be pi. And that's because pi keeps going on and on and on and on. It never stops. And that's what separates an irrational number from a rational number. Rational numbers, whenever they're wrote out as a decimal, they either repeat or they terminate. And terminate just simply means they stop. So with the fraction, for example, 1/2, as a decimal, that's equal to 0.5. Well, that stops at the 5. So that means it terminates after the 5 in that decimal. Maybe one that repeats. Maybe we have the fraction 1/3. That's 0.3, 3, 3, and the 3's just keep going on and on and on. Notice it repeats. The 3 is the number that repeats on and on and on and on. Same thing like maybe if we had, again, this 3/1. Well, as a decimal, that would be wrote as 3.0, or just 3. So that decimal stops. So I'm looking for anything that terminates or repeats, that's a rational number. More of the numbers we've worked with, guys, are rational numbers. Irrational numbers are something new. For example, if I come on my calculator here and I type in pi, it stops at the 4 at the end here, but that doesn't mean that it stops. It's because the calculator doesn't show all the digits for pi. It just keeps going on and on and on. And also notice, in our decimal here, there's no repeating digits. It's 1, 4, 1, 5, 9, 2, 6, 5, 4. There's no repeating or any repetition whatsoever in our numbers here. So that's kind of what separates a rational number and an irrational number. I would encourage each and every one of you guys to look on page 18 in your notes. And I think I've even got it down here at the bottom. Page 18, there is a chart on that page. And it talks about irrational, rational numbers, and it breaks it down. Very similar to how I did in our notes, but a little more in depth. So maybe if you're a little confused by it, it might not be a bad idea to visit that. Our last definition is real numbers. And this is going to be all rational and irrational numbers. So all numbers that fit into the rational and irrational categories, that's going to be a real number. And yes, believe it or not, all jokes aside, there is such thing as an imaginary number. So no, not every number is going to fall into this real number category. You just won't see many of those imaginary numbers yet until we get further in algebra next year. All right, let's begin with some more problems. So with number 6 here, with these 3 problems, guys, I wanted to list off what categories they fell into. So rational, natural, whole, integer, or irrational. And I want to list all of them. So for 15, I'm going to start listing them off. So for 15, is 15 a rational number? Yes, because I can write it as a fraction. It could be 15/1. So it would be rational. Is it a natural number? Well, of course, because natural numbers are all positive whole numbers. So it will be natural. Is it a whole number? Yes. Is it an integer? Yes. Is it a real number? Yes. And the only one that I left off was irrational. It cannot be irrational because it's rational. You can only have one or the other there. And then why is it real? Well, it's real because it's a rational number. So really all of these options, guys, are going to be real. So you don't necessarily have to write the last word there, but you do need to list off every single one of these categories that it falls into. All right, let's look at number 7. We have radical 57. So with radical 57, again, what category does it fall into? Well, radical 57. Can I First off, let's look at the easier ones. Is it a natural number, a whole number, or an integer? No, and that's because nothing times itself gives me radical 57. And if you're unsure of that, come to your calculator, type in radical 57, and there it is. There's your decimal. Now, does this decimal repeat? Does it come to an end? The answer is no. There's no repetition here, and while it might look like it comes to an end, that's because it comes to an end because your calculator cannot go any further. That's as much memory as it has. So because it doesn't fall into any of these categories, it's not a rational number. Radical 57 would be a irrational number. So that one would be irrational. Here's your hint. Any numbers that you take the square root of, just like on this one, if it is not a perfect square, it's automatically irrational. So if the number underneath the radical is not a perfect square, automatically irrational. Last one. Let's look at number 8. So with number 8, we had negative 1.45. On this one, again, it's not natural, it's not whole, and it's not an integer because we have a decimal. So the last thing I'm looking at is it rational or irrational? Well, this is an example of a decimal that comes to an end. It stops at the 5. So because it stops and it comes to an end, this is going to be a rational number. And that's it. That's done. All right. Again, highly encourage you to check out page 18. Check out the chart on the bottom of it. I believe it's a green chart. And kind of look at see how some of those are broke down as well, especially because you don't have any problems to actually solve today and you're just looking at notes. All right, last two problems that we're going to take a look at. So with numbers 9 and number 10, we have two numbers and we need to compare them. I'm not really concerned now if it's rational or irrational. I just want to see which one is greater. Which one of these numbers is larger? In order to compare them, I need them to be the same form. The easiest form to get them into is going to be a decimal. Now, 4 1/3. We all know that 1/3 is going to be 0.3 repeating. So this is going to be 4.3333, and it just keeps going on and on and on. Next, we have radical 17. Well, nothing times itself gives you 17. So I know this is already going to come out to be a decimal. Well, because it's not a perfect square, come over to your calculator, type it in, radical 17, and it gives me 4.123. So I know that 4 1/3 is greater than radical 17. Whenever we write this, we want to leave these in the same form that they're left in. So I'm going to show radical 17, I'm going to show 4 1/3, and I'm going to include my inequality sign in the middle, showing which one is greater or less than the other. So radical 17 is less than 4 1/3, and that would be how we compare those then. So again, make sure they're in the same form. Again, I think decimal is the easiest way to get them in. Let's look at number 10. So number 10, we have radical 129 and 11.52. 11.52 is already in a decimal form. So I just need to get this radical 129 into a decimal. So let's go to my calculator. Radical 129. Type it in, I get 11.35. Something I want you to note, guys, whenever you're typing these in, notice whenever I did my original answer, I didn't write those decimals. I wrote the original form that these were left in. So even though on my calculator it's 11.357, and maybe you're like, Mr. Garrett, you didn't round the 5 up. Well, it really doesn't matter. Matter of fact, I didn't even have to write the 5, because 11.3 and 11.5, I can already tell which one of these numbers is larger just by looking at the first decimal place. So, again, when we write this, I'm going to write it as radical 129. I'm going to write it as 11.52. and 11.52 is larger. So there's my inequality symbol in the middle. And there you have it. Those are your notes for today. So again, a lot of definitions. I would encourage you to make sure that you got all of those down. Visit page 18. And if you have any questions, please let me know. Thanks, guys.